Okay, so we want to talk a little bit about stability. So we have op amps. So here is a picture of an op amp. So it has the two terminals coming in. For our simplest thing, we're just going to take the positive terminal and make that ground. Okay, so basically an op amp is just a high gain amplifier. So let's come over here and look at an amplifier. So here is an amplifier. This is a pretty high gain amplifier. So let's see. So if I put in 1 millivolt and we look at the output, so you see we're getting a pretty high gain here. So this is a high gain amplifier. So in order to create the stability, we want to take this and build it into an op amp. So you see what we're going to be doing is we're just going to add in our feedback resistor up here, and then we're just going to take our output and feed it back over to our input. So we have a 1K right here, we're just going to put a 2K right here, and then we run this. And so the voltage right here you see is 2 millivolts peak to peak. The voltage right here you see is like 4 millivolts peak to peak, so we have a gain of 2. So we took a high gain amplifier and made it into a stabilized controlled amplifier. And so what we see here is that this is the feedback. So this is an inverting configuration. So we're basically, it's going to be like our op amp right here where we're connecting into the middle and then we're building around that feedback. So now we want to look at stability. So let's just look at the amplifier by itself. And we're going to look at the gain properties now. So let's go up to an AC analysis. We'll put in 100, 10, and then we're just going to go all the way out to 100 meg. And so we look at this, and so you see it's nice and flat and then starts to come down right here. We have some coupling capacitors, so there's a corner down here, but it's a lot smaller than what we have here. And then this corner is caused by the internal capacitance of these 3 stages. So we have 3 of those stages. So if I look right here, right in the middle, now we're interested in this phase term right here. So right here, we have 180 degrees because this is an inverting configuration. So it should have 180 degrees out of phase. But then if I look over here, you see that the phase right here is getting smaller and smaller, right? So once I hit this corner, if we look at these corners, so if I have some amplifier that's say A0 over 1 plus JF over F naught, and we have 3 stages, so we're going to cube this. So first of all, if F is much, much less than F naught, so I'm in my mid-band point, then this is just going to go to A0 cubed. But if F is much, much greater than F naught, and then if I do negative right here, so then this is negative right here. So then this is going to go to A naught cubed over J F over F naught. And so what we see here is that we have this phase, so that's like 90 degrees, and then we have 3 of those, so that's basically an extra 270 degrees. So I have 90 degrees per phase that's going to be cubed. So if I go back over here and look at this, you see that my phase is just going down after I get past that corner. So as I get past the corner, I'm going to go down. Eventually, it should go to, but our gain starts to get too high, or our frequency starts to get too high. Eventually, it should go down where this goes down to 270 more than that. Okay, so now what we see here is we can look at the gain as a and the phase as a function of frequency. So there's two things we want to look at. So first of all, we want to say, well, what is the phase when our gain goes to 0? So you see I come down here, and so now you see that my gain went from 60, 64 dB, whatever, or 68 dB, and then it goes down to 0. And then we want to look at what the phase is. So the phase here is 432. And so we went from 180. So we went from 180 degrees to this 432. And so you see, if I look at those two, that that's equal to 252 degrees. And so what ends up happening is that if this is greater than 180, then what happens is that my op amp changed from being inverting to being non-inverting. So this is going to become this. So now it was an inverting configuration right here. Now it becomes a non-inverting configuration. So if I look over here, and the other thing that we want to look at is we want to look, and so this is called the phase margin here. The other thing that we want to do is we want to look at what's called the gain margin. So in that case, I'm trying to figure out what is the gain that I get when it goes to exactly 180 degrees. So we started at 180 degrees, so we're going to 360. So at this point, I've exactly swapped my terminals from inverting to non-inverting, and this occurs at 10 megahertz. So that is called the gain margin. Okay, so let's go and write these down. So gain margin. Okay, so the gain margin is the gain when the phase is equal to the original phase plus 180 degrees. And then we have our phase margin is the phase change when the gain is equal to 0 dB. Okay, and that's going to be whatever the phase is minus my initial phase. And so that's called the phase margin. In order for this to be stable, we want our gain margin to be less than 0 dB. So that means that it's going to get smaller as I go across. So let's come over here and look at what we mean by all of this. Okay, so I can build this. So I'm going to build this back in. So first of all, I want to look at what is the phase here relative to that one. So if I go in and add back in my feedback, so we're going to make this into an op amp. So I put in 2K right here. Oops, we want to go back to the transient. Okay, so the voltage right here is plus or minus 2 millivolts. The voltage here we see is the 4 millivolts. Okay, so that all seems great. It's acting because this term right here, I'm taking my output, feeding it back. It's an inverting, so this is an inverting configuration. So now I'm going to come in here, and I found out that my 180 degree point was at 10 megahertz. So I'm going to make this 10 megahertz. I'm going to change this to be 10 micro. Let's just put in 9 micro here. Okay, so then we run this, and I look right here, and what happened? Well, this isn't just 4 millivolts. My 2 millivolt signal right here became like 20 volts. So what we see here is that this inverting configuration is no longer an inverting configuration. It's actually now a non-inverting, or it has positive feedback instead of negative feedback. So that means I took this 2 millivolt signal and then I amplified it, and then I took this signal and added it. So now I'm going to take the output, add it to the input, and amplify it and amplify it and amplify it. So each time I go around this cycle, it gets bigger and bigger until it basically just saturates. And so we get this whole signal. So what ends up happening is, let's say that I had my signal. Let's make this a little bigger. So let's say that I have my signal that's, let's just say 1 volt. Oops. At my 1 kilohertz. And then I have 1 microvolt at the 10 megahertz. So if I look at my input right, there is my 1 kilohertz signal. And it looks like it's all 1 kilohertz because this little tiny noise signal that's sitting right on top of it, you can hardly even see because it's just noise. You know, if I zoom in, it's hard to see. But there's a little high frequency signal kind of riding on top of that. You know, it's so small that you can't even see it riding on top of it. Okay, but then if I go over here to my output, what you see here is that because we get positive feedback for the 10 megahertz signal, that gets amplified really large. So I couldn't even see that signal because that noise signal was so large. But look, there it is. And so all I see is this teeny tiny noise signal got amplified and amplified and amplified. And so this is called oscillation or ringing of a circuit. And all I had to do was pick up a tiny amount of noise that could be picked up from the air with radio signals or just some random noise by temperature fluctuations in resistors. And so we need to make sure that this is stable. So this is called, this is because my gain margin was all messed up. So let's go back and look at that again one last time. Okay, so in order for this to be stable, we are going to go to the point where I change by 180 degrees. So when I go from 180 to 360. So we have, at this point right here, we have a gain of 33 dB. In order for this to be stable, I need to make sure that this value right here is less than 0 dB. So therefore, when I'm trying to do and I'm feeding back my positive amount, we need to make sure that its value gets smaller every time it gets fed back. So when I change from an inverting to a non-inverting terminals on this op amp, I need to make sure that the gain on each pass or each cycle is less than 1. or less than 0 dB, so that it gets smaller and smaller and smaller rather than bigger and bigger, so that it won't oscillate. And so those terms are called gain and phase margin. So to look at this one more time, we pick the 180-degree point. This gain right here is my gain margin. And then my phase margin is I go to 0 dB and see how much my change in phase is. So 430 minus 180, that is my phase margin. So phase margin is when my gain is 0. What is my phase difference? And then gain margin is when my phase is out by 180 degrees, how much gain I have. And so for it to be stable, my gain margin needs to be less than, my gain margin needs to be way smaller. And so I need to take these corners, I need to either drop my gain, or I need to take this corner and move it back farther.